All right, so I'm going to be doing section 4.1 and 4.2. This will be polynomial functions and their graphs. So a polynomial function is a function of has degree n, which is just matching the highest power you see here. So if it's degree n, it'll be here. So if this was a 5, this would be degree 5. And then it just kind of goes down in descending order. This is the standard way of writing this. Notice that all of these existed, so just real numbers, so it could be 5, 10, 0. 0 is a perfectly valid one except for a to the n, because if a to the n was 0, you'd really have an a to the n minus 1 polynomial. And so n's exist in natural numbers, so these could be any, it can be 1, 2, 3. You don't have x to the 4.5. Once you have x to the 4.5, it's not really a polynomial. I mean, it is, but it isn't. At least not for your definition of this class. These are called the coefficients, right, of the polynomial. A0 is the constant term, an is the leading term, or the leading coefficient, where an, x to the n is the leading term. So let's actually just kind of break this down with a sample. So here I have a sample here. So this polynomial we say is degree 7, right? Because 7 is my highest power on my x. And so we say degree 7. And since that's 7, we also say that this right here, 4x to the 7th, is my leading term. And the leading term is just whatever has the highest power on it. We say 4 is my leading coefficient. And the leading coefficient is more important than all the other coefficients in some ways because it determines the end behavior of your function. Okay, and so here we have this constant. We say I probably should have done this something different. I really should. Let's just say this is, I don't know, an 8 for a second. So I'm going to say 8 is my constant term. This one is also kind of important. My coefficients here are 4, 3, 3, and 8. Okay. And so that's just how we break down. And this is just some vernacular to use. Let me find it on Canvas. Oh, thanks. Yeah. All right. All right. So let me open up something for me because I'm still leaking. All right. Sorry. Okay. So polynomials tend to be continuous out cusps, corners, breaks, or wrong hole. H holes. Draw a function, the things that are polynomials. So polynomials tend to look wavy and they go up and around like this. They can be they could be really funny for a little bit and then come up. That's fine too. Here's a polynomial. What isn't a polynomial by looking at it is all of a sudden you come to this and then you have this or this. So let me go ahead and draw this real quick. It's because we call this a break. So it won't have any breaks. This is a hole. So it won't have any holes. And so, like function doesn't have a value here or here breaks magically. You won't have a cusp, which comes in and comes back out. It kind of, oops, let me do it a little bit better. Our point. It won't have any corners. So we call this a cusp. And this a corner. The difference between a cusp and a corner is just anything sharp. So technically that's a corner, right? And a cusp is something where it kind of sucks in and then it goes out like that. And so it makes a point. Well, corners can be kind of blunt. Cusps are always kind of pointed. Does it really matter between the two? Oh, someone said, no, you're fine. I got you for attendance. Yeah, you're perfectly fine. And so do you need to know the difference between these two? No, because for you, you're never gonna have to distinguish between the two. Because if you see either, you know it's not a polynomial. Now, I can, later on when you look at graphs, this means something different, but you'll never hit that point. I won't say never. Most of you will not hit that point in your careers in mathematics. So don't worry about it, especially now, okay? All right, so let's get into this. So let's talk about the end behavior of the polynomial. So the end behavior of polynomial is should be determined. This shouldn't be that. This should be determined by the degree n and the sign of the coefficient. And so basically we'll have 4 different end behaviors. Let me zoom out so I can do them all at once. So we'll have 4 different end behaviors based off of what's going on. So if it's odd degree, which means like x to the cubed or x to the fifth, right? Or just x is fine. If it has odd and the leading positive leading term, so if it's positive, well, negative values will be negative, right? So x like -10 with cubed is -100, 1,000, right? So it'll be -1,000. And then positive values should be positive, so that'll be a positive value. And so that odd term wins overall, because notice here that no matter what this is, or how big this a to the n and the rest of this is, as n gets relatively large, like 100, 200, 2,000, right, this term's going to win out. Because 2,000 raised to the n power is just going to win everything that's here. And so here it'll come up, it might do something, and then it'll come back out. So for negative values, it'll be negative. For positive values, it'll be positive. And I'll show you a couple samples of this on Desmos in a second, okay? Here, if it has a negative term, it's going to be massively negative, and then it's going to do stuff, and then it's going to come back out. All right, so let me show you a couple examples of these on Desmos. You get a little bit more familiar with like this. Yeah, so Jenny, I got your message and I've already marked you. All right, let me open up Desmos before I move this so I don't have to cut. Oops. All right. My friend showed me the what was it, the South Park episode where like Cartman's like, my internet's acting up, and he goes, and just like puts a picture of himself up and just goes, walks away and eats breakfast. You guys don't even have to do that. I don't make you turn on your cameras. All right, so let's look at this. Let me look at this. Hold on, let me just make it not so crazy. So x to the third minus 4x squared plus 3x. Oops, it should be plus 3x plus 2. So here's a polynomial of degree 3, right? Let's go ahead and make this a minus just for fun. Okay, yeah. So here we have a polynomial of degree 3. And all we really want to know for this right now is end behavior. So notice here that I have a positive, so 3 is a positive coefficient, and this is odd, right? So it's 3. So it comes in from the negative, it does stuff, and then it goes out positive. And notice that if this was a 5, it still acts more or less the same way. And even if these numbers are really large, right, like minus 400x, I mean, that's really large, right? But notice if I zoom out far enough, maybe too far. All right, let's make it less egregiously awful. There we go. Notice here that this is pretty bad, right? Minus 40. And so when you go in, it comes up, but this still wins, right? Even if I made it positive. You think that would have a huge effect, but honestly, it's really not that big because it's still going down. It's going negative on negative and positive up to positive. All right, let's zoom back in, make this less crazy. This is also true for the 7th, right? Now, notice if I switch this to like a -2, we completely change what's going on here. Let's make this less crazy. There we go. We completely changed what's going on here. So now we have a negative number up front. It's going to be negative. So it's going to be positive going out, right? So as we have down here, positive, and then goes down to negative. So the leading term, after this, the leading term completely dictates what's going to happen for our end behavior, right? So if this is negative, it's going to be going negative up. And if it's odd, it'll have, if it starts going up, it'll end going down. If it starts going down, it'll end going up. Okay. So let me just put this aside and let's talk about even behavior. So even behavior are things like x squared, x to the 4th, x to the 6th. Okay, so if it has a positive term, it's going to come in, it's going to do stuff, and then it's going to come back out. And if it's negative, it's going to come in and go back out. Okay. And I'm just drawing squiggles here because it may be really interesting. It may not be that interesting. Okay. So the one you already know for this one is x squared, right? So here, this is an even term, so it goes up and up. And if it was minus, it'd be down and down. So you know the parabola already. But let's make this x to the 4th, right? And let's make this x cubed. See if I can. X squared. Okay, so now I made this a 4th degree polynomial. Okay, so here it starts negative because no matter what's here, eventually when x gets way out here, this term is going to win. This term always will win. And so the negative 4th wins, and then here the negative 4th wins. All right, so because if I plug in a negative number, say like negative 10, right? That's good. Negative 10 to the 4th power is going to be positive, and then I'm going to multiply it by a negative, so it's negative. And here, positive 10 to the 4th power would be positive, multiplied by a negative number, therefore negative. Okay. And so this is the behavior for that. And then if I add it, make it positive, like say 2 or something, and make this negative. There we go. So here we can see that it comes in from the pot. It starts up, does stuff, right? We don't, that's what the little squiggles mean. It means something might happen. Who knows, right? That's what these squiggles mean. And it goes up. So so what's the takeaway from all this? The takeaway is if you have an odd degree polynomial, so if your leading term is a positive degree or odd degree, so like 3 or 5 or 7 or 1, and you have a positive coefficient, it's going to start negative, it's going to do stuff in the middle, then end out positive. And here it's going to start, and if it's negative, it's going to start positive, do stuff, and then end out negative. And for the even degrees, it's a positive leading term, it's going to start positive, do things, and end positive. And for the negative leading term, it's going to start negative, do some things, and end negative. Okay. And so this is the first piece of the puzzle we're going to do when we graph these things. So this is the first thing we want to learn. All right. So real zeros are polynomials. So all these are equivalent. Basically, if this is basically these are all the same definitions for the same thing, right? Kind of like saying the same word for the, like you say feline or cat, means the same, just different connotations, I guess. So here, a c is a zero of a polynomial. So c is a zero of a polynomial. That it also means that x equal to c is a solution to the polynomial equal to 0. So we say the 0. Or x minus c is a factor, so it's something we can factor out. Or c is an x-intercept of the graph. Notice if this is a solution for this being 0, when I plugged in c, I'm going to get back out 0, so my function here would be 0, so it would be one of these intercepts here. So these things are equivalent, so if I say 1, you can use any of these to figure it out. All right, so let's figure out how to do this safely. Immediate value theorem. If P of A and P of B have opposite sign, there must be a 0 between A and B. It's just like, basically it's going off of the continuous. If I was negative and then I'm positive, that means at some point I went through the 0. That's all it really means. I don't think we're going to use that too much. All right, so this is how we graph these things. Let me give me a second just to clear my nose. All right, so this is how we're going to graph these things. It's a little bit of a process, but we'll get through it. All right, so you're going to find the zeros of polynomials and mark these on the graph. So we're going to figure out where my zeros are, and we're going to put zeros everywhere for there. Okay, that's our first step. Our second test, we're going to test points between these zeros and graph those. And so we're just going to test some points in between it and graph them. We're going to determine the end behavior of the graph. And then we're going to fill in the rest of the graph, basically guess the rest. And so let me show you how we're going to do this by hand. You would have to do this by hand if you're doing, if we weren't during the middle of the pandemic, but everything's remote, so no one's doing it by hand right now. But we'll have to use a computer. I suggest having Desmos handy. Don't rely on it completely. Learn the material, of course, that's always my suggestion, but it won't hurt to have it handy, right? All right, so let's look at this. So what are the zeros of this graph? Where is this graph equal to 0? So go ahead and put that into chat. Let me just see if you guys are awake. What values of x produce 0? Yep, someone's awake. All right, so the zeros here are 3, because if I plug 3 into here, I'm going to get a 0. 0 times anything is 0. Minus 3, because I plug in minus 3 here. Anything times this gives you minus 0, and 1. So here are my zeros of the graph. So I know these are zeros. So what I'm going to do, I'm going to put in minus 3, 1, and 3. I'm going to say the value here is 0, 0, and 0, right? So I know that. And so I'm actually going to put those points in. So 1, 2, 3, that's a 0. 1 is a 0, and 1, 2 is a 0. Or 2 more from that would be 3. So 1, 2, 3 would be 0. Oops, someone's drawn on my screen. So, you know, if I was a really good teacher, I'd have you guys, someone else has a mark. If you could you figure out how to get rid of that for me? If I was a really good teacher, I'd have you guys draw it on the screen for me, right? Instead of me doing it for you. But I'm not that good of a teacher. All right. Hold on, let me see something real quick. I have the power to clear all of them. Hey. It's good to know. Live and learn, right? Oops, now I'm annotating. I don't want to annotate. No. Clear all drawings. Go away. I want to use my Photoshop. Thank you. Even if you can't have a... Oh, you... On the notes. Yeah. Well, you guys could do it. I don't know, say I don't trust you guys. Let's put it that way. It's terrible. All right, so we graph all the zeros here, right? So we put in all the zeros. We just want to test points in between it. So an easy point to test is 0. And another easy point would be like 2. One after this would be 4. And one after this would be -4. So I'm just choosing points, right? So these I just choose at random. So here, between 1 and 3, 2 is an easy point. Between 1 and -3, 0 is an easy point. And then I just choose whatever the next whole number is usually for these. So now I'm going to just plug this in. So let's plug in zeros. So x equal to 0 is -3 times +3, which is -9 times -1, which is 9. Everyone see where I get this 9? Any questions on that? At least you're honest. Fair enough. Here, if I plug in 2 minus 3 is 1, or -1, right? 2 plus 3 is +5. 2 minus 1 is 1, and so I get -5. So here I have 9 minus 5 for -4. So go ahead. So I'm going to do, oops, I'm on the wrong layer. Of course. So what do you get if you plug in 4? I'm going to do -4. You guys tell me what 4 is. So -4 is -35. So if I plugged in 4, what do you get? So just put it in here. So it'd be 4 minus 3, 4 plus 3, and then 4 minus 1. And I'll give you a number. And we get what the value is for 4. Yeah, 21 is correct. All right, so 21. Because we get 4 minus 3, which would be 1, so +1. This becomes 7, and this becomes 4 minus 1, which gives us 3. So 1 times 7 is 7. 7 times 3 is 21. All right. So let's determine the end behavior of my graph. So here I don't have what this is. So you have two options. Let's have two options here. So the leading term. So you could just take the leading term here and multiply it together. And so here I get x times x times x. So the leading term would be x cubed with a 1. And so this is positive and odd. So I know my end behavior looks like this, right, from my previous graph. Looks like this. So you can just take the largest value of each of these and multiply it together, or you could just type it in. Let me show you how to type this in. Wolfram alpha. Yeah, I'm okay to leave decimals for a second. Oh, I probably should have left it up. History. That's fine. Whee. All right, so let's look at this. And so you just type in expand a polynomial. Actually, expand polynomial, and then you'll have x minus 3, x plus 3, and then x minus 1. In fact, I don't think you need the word polynomial. I think you just type in expand, and it knows what you want. Yeah. And so here you can just expand it. And so we see the leading term is this. All right, so we know what the behavior is, and so now I can graph it. And notice here that when we test these points on the outside, so 9, so this is 8, so 9 would be slightly above it. 2 would be -5, 1, 2, 3, 4, 5. And then 21 is way above it, and -35 is way below it. So it's going to come in, roughly go through this point, come up, go down, go through this point, come up, go down, and head on out. Okay. And so this is my rough graph of this. And notice the end behavior looks like what I suspect it should, right? It's down, the stuff in the middle goes up. I marked all my zeros at 0, I know it's 9. At 2, I know it's -5. The rest of this is a guess. Like, this is probably wrong, but it's a guess. But let's look how it looks like in Desmos. Well, let's look at the graph in Desmos. Ta-da! So this looks really close to what we just drew, right? Excessively close. I mean, here's the 0, 3, here's the 1, here's the 2, here's the 2, here's the 2, -5, right? It actually is a little bit, the lowest point is a little bit to the right of that. Here's our 0 and 9. Here's actually the other minimum point. And we don't calculate that. And so this is really kind of close. And so even though we did it by hand, we got really close. All right, so let's do this again. Let's look at this one. All right, so I'm going to graph this using the guidelines we've had before. All right, so same rules, same guidelines. So the first thing we want to do is find the zeros. Well, how do we do that? Well, you don't know the zeros by looking at this, but here I notice I can pull out an x. Everyone okay with this? X squared minus 2x, oops, just 2x minus 3. Is everyone okay how I just factor down an x of each of these terms? Yes, no, maybe? Yeah, okay. I mean, I used to have people, if I was in a live class, of like, if we don't understand what just happened, wink
and
at
she
me.
said, hey,
No one's
Jay
gonna
Bird,
raise their
in order to
hand,
stay calm, grab
no
my
one's gonna
phone
notice
and
you
just
winking
call
real
911.
quick.
Let's see when we get service. She
So I
keeps
used to
driving
do
and
that.
she's like, you only have 1% battery. I know, it's okay. Just keep using it, okay? She says, okay. As they're driving, they hit snow.
I just hit the little mute button on everybody. If you want to talk about class, by all means, go for it, right? And until then, we'll just go ahead and keep people on mute. All right. So here we do this. Then we can factor this, and so this becomes x minus 3, x plus 1. Oops, my plus looks a little weird. Back up. Right on the right layer. X minus 3, x plus 1. All right, so now I have my zeros. My zeros here are 0, positive 3, and negative 1. What's my leading term? My leading term here, again, is x cubed. And so I know it should look like this, vaguely, right? So it should start from down and go up. We'll plug in our zeros. So this would be minus 1. This would be 0. This would be 3. So minus 1, 0, and 3. So this is 0, 0, and 0. So I know I have a 0 here, right on the x-axis. So right at the origin. Negative 1 is also 0. And then 3 is 1, 2, 3. And that's also 0. All right, for my points, I'm going to choose 1. There's no whole number, so I'll do negative 0.5. I'll just do minus 2 here. And then 3, I'll just go to 4. All right, so the easiest way to do this is just to plug these values into here. I think it's easiest just to do this in your head. So if we did 1, I'll have 1 minus 2 times 2, it would be negative 4. I'll have 4 times 1, which is 4, times 5, which would be 20. The 0.5, that's what a calculator is for. I already pre-calculated it at 8.75, 0.875, and the negative 2, so it'll be minus 2, minus 5, minus 1, and so that'd be minus 10. Okay, so minus 2, I'm at minus 10, so I'm way down here. Here I'm a little bit less than 1. At the negative 0.5, at 1, I'm at minus 4. 2, 3, 4. Here I'm at 0. And notice my behavior. So it's going to come in from the bottom. I know that because of the leading term is positive. This is the same as 1x cubed. So it's positive odd, so it's going to come up. It's going to come in like this, go down, probably go down a little bit further, then come back up and then shoot on out. Okay. Besides the fact that I accidentally, I'm going to fix this up just a little bit, made it not a function. There we go. That's better. So let's see what it really is. So we'll just go ahead and type this right on in. And I have x cubed minus 2x squared minus 3x. Yeah, that's it. And notice what we have here. Look how close this looks, right? I mean, is it exact? No, but here's this, here's that. I mean, we're really close to that point. Here's that. We didn't get that point, but when we guesstimated, it wasn't that far off, right? It goes up and goes through. And so so even though we're doing this by hand, we're getting really good close results. So let's do another one with you, and then I'm going to teach you a couple tricks. A trick real quick, how to do it for very large ones, and then we'll go from there. Okay? All right. So let's look at this one. We'll probably finish these notes today and go a little bit long today and then be short tomorrow. But technically, I think I'm supposed to go an hour and 15 minutes today and then only 50 minutes tomorrow. So it's perfect. Works out perfectly as scheduled. All right, so let's look at this one. All right, so my leading term on this one is different, right? Here I have a leading term of minus 2/4, or 2x to the 4th. And so I know it's going to come in at the negative, do stuff, and then go back down. How do I know that? It's because it's even and negative, and so it's going to look like this. You'll get used to what these look like after you do the homework. Once you've done enough of them, you'll just have it in your brain. All right, so this is what the graph should vaguely look like. Let's just find our zeros. Well, our zeros, here we can pull out a negative x squared. That'll leave me with 2x squared plus x minus 3. And then I can factor that. So it'll be minus 2x squared minus 2x plus 3, x minus 1. Okay, so that's one way of factoring it. You can always, if you ever get super lost while you're doing your homework, it's good to do it by hand. But if you ever get super lost while doing your homework, expand will tell you, we'll take your factors and do it out. We just type in factor, and I'll just type in minus 2x to the 4th. I don't remember what were. Minus x cubed plus 3x squared. So if you just type in factor, it'll do, and we got the same result, okay? And notice here, this will give us our zeros. And so you can also type in zeros. I'll give you the zeros. And here we'll get the zeros of 0, 1, and minus 3, 2. And that's the same zeros we got here. Because negative x squared, that 0 is a 0. This one, the 0 is, so if I had 2x minus 3 equal to 0, that means, or plus 3, means 2x is equal to minus 3, or x equals to minus 3 over 2. So that's the minus 3 over 2, 0. And this, of course, is the 1. Okay. So I have a 0 of a 0, negative 3 halves, and then 1. So I'm going to plug those in order. So this would be minus 3 halves. This would be 0, this would be 1. I know what the values are, 0 and 0 and 0. So 3/2 is negative 1.5. It's the same. This is also minus 1.5. More comfortable with that. 0 and then 1. And we're going to test points in between them. So I'm going to test negative 1. 0.5, there is no whole number, so we'll just put in 0.5. We'll do 2, and then we'll do minus 2. At this point, I assume you can crunch these numbers somehow, so I'll just give you the answer. So it's 12, 2, 0.5, and minus 28. So we'll just plug those in. So that's way off the graph. That's way off the graph. At negative 1, it's positive 2, so right about here. And then at 0.5 is 0.5. Okay, so we'll just go ahead and draw this in. Comes in, then it comes here, and then comes up, and goes down. Okay. So it looks like a weird looking M. And is this exactly what we predicted it to look like? Yes. All right, now let's do it in Desmos. And then I'm going to teach you one last trick to graph these things. And we'll go from there. All right, so what do I want? I already have it typed in. No reason to type it in. Command copy. Whoa, command paste. Presto. And look, that's exactly what ours looks like, right? Ours looks very much like this. And so even though we're roughly estimating these graphs, we are doing a very good job at it. Okay, so I want to draw your attention. Notice here, at this point, the graph did not go through, right? Usually at my zeros, I've gone through every time, but here I did not. I kind of just hit the origin and bounced and gone through. And the reason is that this 0 is technically a double zero. X squared here. We could really write this in minus 1 times an x times an x times. I can get rid of this real quick. Times 2x plus 3. And so we say that this 0 has multiplicity. Can you show example 5 again? Oh yeah, I can. Let me just zoom out as I'm talking. So here we say that this 0 has multiplicity of 2, right? Because it appears twice. Because this is 0 and this is 0, and so we have multiplicity of 2. And so what happens is if you have an odd multiplicity, like 1 multiplicity of 1, you'll go through the origin. If you have a multiplicity of 2, it'll kind of bounce at the x-axis. And so now we can graph something completely crazy with using this theory. Okay. All right, so I'm gonna go to the last page. Let me show you this. All right, so the number of times that x minus c factors upon is the multiplicity of that 0. So if I can, so here I had x minus 0, which is just x. This factored this twice, right? I could pull out one x, and then I could pull out another x. And so that it came out twice in this case. And so there's multiplicity of 2. If the multiplicity of 0 is odd, the graph will cross the x-axis. If it even, it will not. And so usually I say it crosses or it bounces, right? And that's what I usually say. It'll bounce. So here we have this huge beast, right? This thing is just huge, right? And we're gonna graph this even. Let's say I can say this even more roughly, right? Even more roughly. So what am I? And so here I'm gonna swap out this. I want to use something else. So this is my 0. I want to use this to be my multiplicity. Okay, of that 0. I'll just choose mults. Okay, so my zeros in this case are 0. This one will be, hold on, let me do them in order. So I'll have -1, right? I'll have 0, and then I'll have +2. Now, how many times do I have the 0? Well, I have it 4 times, right? So that's multiplicity of 4. So we're not doing the graph, we're doing multiplicity of that. And so this is even, and so it bounces. Okay, here, how many times do I have the 1? I have it twice, so that's multiplicity of 2. So this is even, and it'll bounce. And here at the 2, I have it 3 times, so this is 3 times, so it's odd, and it will cross. All right, and what's my leading coefficient? Well, my leading coefficient in this case is x to the 4th times x cubed plus times x squared. Or you could just type it into Wolfram alpha. Let me just go ahead and show you how to do that as well. And here we'll just go to here. So expand x to the 4th x minus 2 cubed, sorry, x plus 1 squared. All right, so we get x to the 9th, okay? And that's the same thing we got here. So notice if you just take the largest value, so here if I just cube this one, I'll get x cubed. And here if I just square this one, I'll get x squared. You'll get x to the 9th. And if I add all this up, I'll get 4 plus 5 plus so x to the 9th. So I know my behavior is the following: x to the 9th, and it's positive, so it should come up, do stuff, and go out. And actually, that's all I really need. And let me explain why that's all you really need. So here I have a 0 at -1. I have a 0 at 0. And I have a 0 at 2. I know at -1, it's going to come. It's going to come in, but it's not going to cross the x-axis. Why? Because it's an even multiplicity. So it bounces. It's going to come into 0. It's also not going to cross that. It'll bounce again. And then at 2, it'll go through, and this time it will cross and come on through. And there's my graph. Okay. And so this is just a really rough way of graphing it, but it ends up being even more rough than what we've been doing. But however, it is super accurate, as I will show you. So let's go ahead and click this. Hi, can I have this, please? No, you're not going to like me. Fine, can I just type this in the Desmos and it knows what I'm doing? We will find out. Yep. All right, so notice here, this is what we have. Is it somewhat like this? Yeah. Is it exactly like that? No, right? But it's not a bad estimate. It comes in, bounces a little harder, and then heads on out. And so here, you can just use the multiplicity of zeros to roughly guess this. And notice we could do the same thing here. So here, let's pretend we didn't know what was going on. Let's just quickly look at this. I know I have a 0 here, and it has a multiplicity. So let's just put in a multiplicity of the 0. So this is multiplicity of 1, so that's odd. So it's going to cross. This is a multiplicity of 2. Notice we had this one twice. That's even. It's going to bounce. And then here I have the multiplicity of 1. So that's odd. It's going to cross. And so which way do I know it's going to happen? It's going to start coming in from negative. Here, I hit my odd. I go through, come down. Here I hit my even multiplicity, 0, bounce. And then here I hit my odd and go through. So here's another example of that. The one above it isn't as interesting because all of these have multiplicity of 1. So the multiplicity of 1, so these are all odd. And so they always cross. But you notice here it still works. I cross, I cross, I cross, and I'm done. Okay? And so using the multiplicity of your zeros is the fastest way. Yes. So using multiplicity of 0 is the fastest way in order to roughly estimate what the graph looks like. Okay. Let's see what the question is. So we're not trying to get the graph to be 100% accurate as long as we have the 0 and multiplicity. Okay. Is the homework going to look like the graphs, or is it going to be exact? We'll deal with the homework exclusively next time with you guys. I think the homework, some of them it's graphing, some of it's just choose the right graph. But if you know where the zeros are at and you know if it goes through or not, you can almost guarantee it's going to. That's all the question as accurate as you need to be. Okay. I'll open up the homework in 1 second. Let's just finish this real quick. All right. So number of local extrema. So the number of local extrema. So if polynomial degree n, the graph has it n at most n minus 1 local extrema. And so the number of how many local mins or maxes a graph can have is 1 minus that. So for the quadratic, which you guys know, it only had, which is x squared, it could have at most 1, right? It could have 1. It is either a min or max. For a linear equation, there is no local extrema, right? So that's x minus 1. So x1 minus 1 is 0, so 0 local extreme. 2 minus 2 is 1, so that was 1 local extreme. For a cubic graph, you can have at most 2, and it goes onwards. So for this graph, it's x to the 5th is the highest, right? And so this can have at most 4 local extremes, right? For this one, x to the 4th, this will be 3 local extremes, and here we have this, which we've already addressed to be 1. So that's the max number of local extremes.